Aaron, I think you have the microphone.
Hi everyone, my name is Yimeng. So I'm a graduate here in UC course. So it's quite a great pleasure to share my work here. So I'm going to talk about the connection between Dwarf Galaxies and Globular cluster and our new insight from the Perseus cluster. We know the Globular cluster are all massive, dense star clusters, and we can find them in all kinds of galaxies from giants to dwarfs. And here's just an example, like the Globular cluster in Fornax dwarf, a satellite of our Milky Way. In the studies of nearby galaxies, we have built a scaling law relation between the GC system and the host galaxies. So the y-axis is the GC system mass versus the galaxy stellar mass, and the x-axis is the galaxy stellar mass. So you can see from our Milky Way to the dwarf galaxy region, the mGC over m stellar mass just increased dramatically. And we generally think this is just a mirror image of the stellar mass halo mass relation. But I think the basic question here for the dwarf galaxies is why we have a big scatter in GC richness, i.e. the y-axis. We know partially it's because you have a diversity in halo, but is that the only reason? So people have investigated that a lot. So first, people have explored the environmental effect. So the right-hand figure shows the GC richness over the cluster central radius for Virgo dwarfs. So the Peng et al. 28 find the dwarfs galaxies near the cluster center have are generally more GC rich. So people find this is easier to understand because the dwarfs near the center form early, and at the time you have more dense gas to support the GC formation, and they also quench earlier before because you lose your gas and you reduce your stellar mass, and the galaxies in the lower density environment just do things in the opposite way. And here's another finding just in recent years, the ultra diffuse galaxies. So many UDGs, they have distinctly more GC-rich population. Like for example, these galaxies, you can see almost all these white dots are Globular clusters. And also more generally, as shown the right pole shown, its GC richness over surface brightness. Generally, both galaxies with lower surface brightness, they are on average more GC rich, but this trend they did not control for mass. So I have to emphasize, we have lots of fantastic studies here, but until now these studies in this field are still very incomplete. Because these people have, generally we have been using very limited samples, and mainly from Virgo and Coma clusters. We have very limited sample size, and people have been using very different data sets, very different methods, very inhomogeneous analysis. So you cannot simply say, I put everything together and do some statistics, because you have all kinds of systematics. So we want to address those points. We want to explore other environments. We also do some homogeneous analysis. So we put our eye on Perseus cluster. So Perseus cluster actually is the coldest high mass galaxy cluster. Why we didn't explore this? Because Perseus cluster is at the low galactic latitude, so you have a lot of dust. So Perseus didn't get enough attention until we got the large field image data until recently from Subaru and Euclid. So this image is a very beautiful imaging from Euclid. So talk a bit about our study. So we select 190 dwarf galaxies with stellar mass from 10 to 7 to 9.5, we've seen 0.5 barrier radius. So we got galaxy photometry from Subaru, HSC, and we measured the GC system also from HSC and supplemented from HST and Euclid. And we have the velocity measurement mainly from KEC, and also some of them get their velocity from literature. So I have to emphasize this is the largest data set of the dwarf galaxy in one single galaxy cluster with the photometry, spectroscopy, and GC count simultaneously. And on the right side, just the spatial distribution in the Perseus cluster. And this is just shows the our sample distribution of our sample in some basic parameter space. So on the left side is the color magnitude relation. Basically, our sample is on the red sequence. So just want to show those galaxy clusters, the star clusters are GCs. And the mass range, yeah, just as I said, 7 to 9.5. And on the right side is a size magnitude distribution. So we do have some UDGs, but I'm not going to talk about that in this talk. But generally, our sample has a relatively wide and uniform distribution in the parameter space, and which is actually much better if you compare to previous studies in Virgo and Coma. So talk about the result. So the first result just come with this, the y-axis and the GC mass fraction, the GC mass over the stellar mass, and the x-axis is the stellar mass. So this plot itself, the correlation is not interesting, but what we really care about is how about this compared to other galaxy clusters. But as I mentioned, we actually don't have enough data points from other galaxy clusters. So there's another way to make the comparison. So we compare a stellar mass halo mass relation derived from other galaxy cluster. So there's a nice stellar mass halo mass relation from Zaraski and Bruzzi 2023. So that stellar mass halo mass relation is derived from other cluster dwarf, from Virgo, Fornas, Coma, Hydra. Actually, all of them are from nearby galaxy cluster, but they use abundance matching. And we assume a fixed MGC over M halo. So if you believe that MGC over M halo is fixed is a constant for all other galaxy cluster, and you can see our data is actually perfectly fit the stellar mass halo mass relation from ZB23. So you can say there's just no significant difference between Perseus and other galaxy cluster in GC richness for the dwarf galaxies. And the next, we explore the correlation between GC richness and surface brightness. So a similar trend has been found in Coma, so this is a pretty nice trend. But as I said, we really want to do is to compare the things at the same mass. So we need to define GC richness without mass dependence. So we define a delta mass by as a residual of log SM. Just remove the best fit from the mass plot. So we just remake this plot, delta SM over versus surface brightness. So you can still see the trend, although the trend is much weaker, but still very significant. So this suggests at the fixed mass, dwarf galaxies with lower surface brightness are more GC rich. So this is actually the first time people have ever made this plot. And we want to expand this. So there could be two explanations. So first, dwarf galaxies with lower surface brightness, they may actually have a higher density at the time when they form. And they just expand a lot because of the feedback or tidal heating, or their GCs get more disruption if they have higher surface brightness. And then we find Perseus start to behave very differently if we plot the GC richness versus environments when compared to Virgo and Coma. So as I said earlier, we found there's a strong correlation between GC regions and concentric radius in Virgo and Coma, but we found nothing in Perseus. But there's a warning, like we only have the data within 0.5 Vero radius, so we definitely need the data beyond that radius to confirm this trend. But if you only plot the data within 0.5 Vero radius for Virgos, you'll see the trend. So that definitely means there's a difference between Virgo and Perseus. Another interesting point to think about is we see something interesting in simulations. So we check TNG50, TNG100, and Eagle E-mosaics. These three cosmological simulations just predict completely different trends. Especially TNG50 is different from the other trends. So I can talk more about these simulations. So in TNG50, we actually select the one halo with the 2 times 10 to the 14 solar mass. It's actually the most massive halo in TNG50. So it's about Virgo mass. So TNG50 has the most different GC modeling method compared to the other two. So they use a GC tagging method, and every GC has the same mass. And you have to make sure that every galaxy have their GC mass match the scaling relation, as I showed at the very earlier of my talk. And they only have the GC stripping mechanism. They didn't include any disruption, so you can only lose single GCs instead of like you lose any mass within a GC. So for TNG100, so the halos are a little bit more massive than TNG50, so it's closer to Perseus, and the GC modeling is like more standard. You have all kinds of mechanism there. So for E-mosaics, the halos is much less massive, but that's the best we can do. And the modeling is a little bit better than TNG100 because they treat the star cluster as also subgrid components instead of just the very simple particles. But if you see the trend, so TNG100 and E-mosaics predict similar trend. So that is as expect as what we traditionally think about. You have more GC-rich dwarf galaxies near the center. So TNG50 is just completely different. We might think about maybe you have too strong like GC stripping near the center, so producing a different trend. So I think there's just something more to think about, like why there's just so much difference in the simulation. But go back to the observation. If the trend in Perseus, based on our observation, is real, this might suggest like more complex and diverse evolutionary paths of the Perseus dwarfs compared to Virgo Coma or cosmological simulation. And the question would be, especially for the simulators here, if we simulate more galaxy clusters, can we see a case like Perseus? Yeah. So here's just my takeaways. So I will end here and take questions. Thank you.
Questions?
You mentioned the possibility that the dwarfs have a bursty nature that might be related to its sizes, for example. Is that something that the theorists are able to check for you, so that, because the burstiness, you can imagine, also would blow away the gas, and therefore make it much more low surface brightness, and therefore if they're big and low, maybe they're indication that they had a lot more bursty behavior in the past, and there were groups of them. picking up what the theorists say. Is that possible? You have bigger dwarfs?
I'm not sure. I don't know.
Sorry, I didn't get too much about the question.
I'm just asking whether there's a relationship between the surface brightness and the number of globular clusters that's related to the bursty behavior. So there's correlation. The theorists should help answer that question, whether they have found any correlation between them.
I don't think that they have an answer to your question. Yeah. Okay. More questions? If not, let's thank Yimeng again.